Welcome to the session on bootstrapping. This is part of FRM Part 1 Quantitative Analysis. So bootstrapping essentially is a mechanism by which one typically constructs a spot yield curve or a zero coupon yield curve from a normal yield curve. So we'll get into those details a bit later. So we'll discuss about normal yield curve, or short form is NYC, a spot yield curve or zero coupon yield curve, acronym ZCYC, the bootstrapping mechanism itself, and forward yield curve of FYC. So the normal yield curve essentially is a graphical representation of the yields for various tenors. So that's essentially what is called as a normal yield curve. And as you all know, that yield is the returns available on the debt market instrument, for example, a bond. And so generally, the normal yield curve is the curve generated by the yields on coupon-bearing instruments, because that's where the most of the bonds available in the market are coupon-bearing instruments. That means they provide regular coupon or for the investor or the holder of the bond. So for pricing and valuation purpose, one requires a spot yield curve or a zero coupon yield curve. So a spot yield or a zero coupon yield essentially is a yield provided by a zero coupon bond. And zero coupon bond essentially is a bond which produces only one cash flow at the maturity. So there is no intermittent cash flows. So typically what happens is that generating a spot yield curve or zero coupon yield curve from the market is very difficult since there aren't many zero coupon bonds available in the market. And the yield curves typically which is available in the market are the normal yield curves, and from the normal yield curves, the spot yield curve or zero coupon yield curve needs to be constructed, which are used for pricing and valuation of instruments. And we have seen that for inflationary market, that means where there is positive inflation, the normal yield curve is upward sloping, since higher tenor bonds provide higher yields. So in that case, as compared to yields of lower tenor bonds. So let's see an example. So we have taken the yields for US Treasury. So we have taken the tenors up to 1 to years, 2 years, up to 10 years and beyond. And in the column B, we have mentioned as a normal yield curve, which is yields which are for particular tenors in percentage wise. And from this, we need to compute the spot yield curve or the zero coupon yield curve using this particular method called bootstrapping. So we'll come into the particulars of bootstrapping slightly later. Before that, we just explain the concept of the spot yield curve or the zero coupon yield curve. So the spot yield curve or zero coupon yield curve is a graphical representation of the spot yields or the zero coupon yields of bonds for various tenors. And the zero coupon bond is typical a type of bond with one cash flow at maturity. Usually they are issued at discount and redeemed at par value on maturity, thereby producing the returns. And the gradient of a spot yield curve or zero coupon curve in an inflation environment is upward sloping. And since bonds of higher tenors are expected to provide higher returns as compared to bonds of lower tenors. In fact, the gradient of spot yield curve or zero coupon yield curve in case of inflation environment or upward sloping yield curve is still higher than the gradient of a normal yield curve. And since risk in zero coupon bonds is higher as compared to the coupon bearing bonds, as they receive the cash flows only at maturity, so a zero coupon bond is expected to provide the higher returns as compared to a similar maturity coupon bearing bond in the inflation market. So we know that risk and return go hand in hand. So if we have more risk in the zero coupon bond, the returns or the yields expected also are higher as compared to a normal coupon bearing bond. So getting zero coupon yield curve from the market is difficult, as we mentioned earlier, that since there are not many zero coupon bonds available in the market, and hence they need to be derived by some technique, which is what is called as bootstrapping. Bootstrapping is one of the techniques which are used to compute a zero coupon yield curve or a spot yield curve from a normal yield curve. So let's come to the bootstrapping part. So bootstrapping is a method of deriving the zero coupon curve. So we can derive the theoretical term structure from the yield curve using a procedure which is called bootstrapping, and utilizing available spot rates to compute the components of the bond. So if suppose P is the price of the bond or the par value of the bond, and C1 is a first year cash flow. So if we take 100 as a par value, and C1 will be the first year cash flow, that is the yield, first year yield. That means on 100 par value, how much you will get the returns. N is the face value. And so after 1 year, you'll get a cash flow of C1 plus N, which is in fact multiplied by Z1, which is the first year discount factor using the zero coupon yield. And you solve SZ1, which is a first year discount factor, you get P divided by C1 plus N, and from there you get the zero coupon yield. Let's see this in a particular example. So in this case, so we take some assumption that the first year zero coupon yield or the spot yield is the same as a normal yield curve, which is a fair assumption because 1 year the money market funds are there where there is a single cash flow. So the first year normal yield curve and spot yield curve can be considered as the same. Now the second year, this we need to compute. So how we need to compute? As you can see here in this particular spreadsheet, we have a column E, which is a discount factor. We are using a discrete compounding. As you can see in this particular the formula, it is we're using this particular function, that's 1 divided by 1 plus rate of return or yield. Be careful that we are using the spot yield or the zero coupon yield. Be careful to mention the percentage. If percentage is not mentioned already in the number, this in this column C, these are numbers, it's mentioned as numbers. Raised to the power A2, which is a tenor. These are the discount factors. Similarly, we can compute the discount factors for all the tenors based on the spot yield curves which are being generated here in this column C. We'll generate this spot yield curve by some technique. What is the technique? So for that, I'll ask you to refer to this particular column F. So as you can see, this is a par value. So it is a par value in the sense, in this case, same as a face value, which is 100. Now, as you can see, the first particular expression, it is mentioned as B2, which is the first year yield, 0.1120 plus 100, which is considered as a par value. So after 1 year, so if the yield of 1 year is 0.1120 percentage, so after 1 year on 100, you are getting 100 plus 0.1120. So this cash flow is multiplied by the respective discount factor, which is given in E2, which is in this case computed as 0.9989. And the resultant term is essentially a par value, which is essentially 100. Now here in this case of various calculators, there are various ways to compute this par value. In Microsoft Excel, we have something called solver, and also there's something called goal seek in what if analysis. Both these tabs are available in this data particular tab. So solver is much more precise, whereas goal seek is slightly more approximate. So in this case, what we can do is that we can solve the parameters, set the objective. That means what we want to, the objective is, in this case, say we put the value as F2, equal to the value of, click on this button, to 100, which is the par value, by changing cell. What cell? So here in this case, suppose this cell was not there, the C3, which is a 2-year spot rate, was not there. So we mentioned that by changing the variable cell, the C3, and then you say solve, and the computer calculates a particular solution, and you can keep this solver solution. And this particular value is arrived at the spot rates. As you can see here, the difference between the normal yield and spot rate for the initial, the years are very small because these numbers are quite less. If you can kind of make the increase the decimal numbers, you can see that there's difference between the numbers here. As you can see, the second year, the normal yield curve is the 0.123 followed by 5 zeros, whereas the spot yield is 0.123000705. So those numbers essentially increases as you go for various tenors. So similarly, what you do is that for the after the first year is calculated, you calculate the second year, because you require for the second year you require the first year discount factors, uh, and then you calculate the second year discount factors. So as you can see in the second year, if you can see the expression, there are two terms here now. So what happens is that the second year normal yield curve is considered 0.123, which means that second year is returning 0.123. So a 2-year bond, first year on 100 is giving 0.123. So 0.123 is multiplied by the first year discount factor, in this case E2, which is 0.9989, and the present value of the first year cash flow is calculated with this first expression. And after 2 years, you're getting the face value also. So after 2 years, you're getting the second year, you're getting 0.123 plus 100. So that is multiplied by the second year discount factor, and the second expression gives the present value of the second year cash flows. So combining these two present values, you should be ideally getting 100 or par value. If you're not getting 100 or par value, you can use this particular solver, and then you solve for the second year par value, which is in this case F3, value of 100, mention this value 100 by changing the cell, because you are trying to find out the now the third year ZCYC. So you can calculate so accordingly the various factors, and accordingly you can make this particular changes. And so as you can see that you need to do it on a recursive basis. You cannot directly jump to the 5th or a 10th tenor unless you calculate the ZCYCs for the initial tenors. So then you calculate and you find out that particular this value, that how much will be the value of that particular ZCYC. So in this case, so this you do it on a continuous basis, and then you find out the ZCYCs for all the tenors. So as you can see, if you plot this particular graph numbers in a graphical format also, as you can see here, since the normal yield curve and spot yield curve was very close to each other, in fact the spot yield curve is almost red line is there, which is again, but that shows the spot yield curve is the gradient is above the normal yield curve. And we also have what is called the forward yield curve. So forward yield curve essentially, so this is in this bootstrapping mechanism, this is the process goes on indefinitely till the time you complete the entire term structure. So the beauty of this process is that it's essentially you need to start from the very basic tenor and then go on calculating year after year. You cannot directly jump to the 5th or a 10th or 20th tenor in order to calculate the spot yield curve. You need to do it in a particular manner. Now, what is forward yield curve? So forward yield curve is essentially a spot yield curve or a zero coupon yield curve at a future period of time. So for example, a zero coupon yield curve after 1 year is considered as a 1-year forward yield curve. So why are these required? So these are required to essentially to compute the pricing and valuation of various swaps, like say interest rate swaps. We'll see in a subsequent video how to price and value interest rate swaps. So for example, sorry, so to compute the 1-year rate after 1 year, so one requires the present 1-year and 2-year rates. And with no interest rate arbitrage principle, the value of an investment, if you invest for 1 year and reinvest for another year, should be the same as if invested directly for the 2 years. And if you use, if you generalize this and use discrete compounding, if you had invested P amount initially, and after 1 year, it will be P into 1 plus Y1 raised to the power T1, where Y1 is a shorter tenor yield and T1 is a shorter tenor. And if you are reinvesting this for a further period between T1 and T2 at the rate Y12, which we need to calculate, so this itself will be the principal that is multiplied by 1 plus Y12 raised to the power difference between T2 and T1. So this whole amount should ideally be equal to, if you had invested P amount of funds up to T2 time period at Y2 rate of interest. So P is the principal, Y1 is a shorter tenor yield, and Y2 is a longer tenor yield. And T1 is a shorter tenor, and T2 is a longer tenor. So Y12 is a yield from the shorter tenor to longer tenor, which is a forward yield curve. That means the yield from first year to second year. So we have from this equation 1 plus Y12 raised to the power T2 minus T1 is equal to 1 plus Y2 raised to the power T2 divided by 1 plus Y1 raised to the power T1, which can be considered as df1 by df2, which is df1 is discount factor 1 and df2 is a discount factor 2 using discrete compounding. So we can compute y12 as df1 by df2 whole raised to the power. If this t2 minus t1 comes on the right hand side, it becomes 1 divided by t2 minus t1, and 1 goes on the right hand side, it becomes minus 1, and so on. So similarly, you can calculate y23, y34, y45, and so on and so forth. That is 1 year rate after 1 year, 1 year rate after 2 years, 1 year rate after 3 years, and so on and so forth. So this is same thing is being done here in this forward yield curve. So as you can see here, the same expression which we had earlier. So discount factor 1 divided by discount factor 2 given in E2 and E3 raised to 1 divided by T2 minus T1, which is given in A3 and A2 minus 1. The last 100 is just to convert that into a number, otherwise it will be in percentages. So as you can see, the same expression is provided here in this particular presentation. So is that discount factor 1 divided by discount factor 2 raised to the power 1 divided by T2 minus T1 minus 1. So it's the same expression is used here. Discount factor 1 divided by discount factor 2 raised to the power 1 divided by T2 minus T1 minus 1 into 100. So this goes on continuously, and as you can see here, these are the forward yield curve after 1 year. That means this is a 1 year rate after 1 year. This is a 2 year rate after 1 year. This is a 3 year rate after 1 year. This is a 4 year rate after 1 year. This is a 5 year rate after 1 year, and so on and so forth. That means, in short, this is a spot yield curve after 1 year. So spot yield curve after 1 year from today is what is called as a forward yield curve. So forward yield curve after 1 year is essentially the spot yield curve after 1 year. And as you can see here, for upper sloping curve, the spot yield curve, forward yield curve, the gradient is still at a higher gradient than the spot yield curve or zero coupon yield curve, which itself is at a higher gradient than the normal yield curve. So with this, we come to the end of this particular presentation on bootstrapping.